Hello, friend. Some nights feel different, don't they? The air holds its breath a little longer. Stars seem to pulse with secrets they have kept for billions of years. And somewhere far beyond the warmth of our world, something ancient stirs in the darkness. On December 28, 2019, while most of us were preparing to welcome a new decade, two robotic eyes in Hawaii caught a whisper of light that didn't belong. It was faint, almost invisible, drifting through the constellation Ursa Major. But it carried a question that would captivate astronomers for months to come. What if this visitor wasn't from our sun's family at all? What if it had wandered here from another star carrying stories written in ice, older than our solar system itself? Before we drift into this cosmic mystery together, if you find comfort in these quiet journeys through space and time, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. The Atlas telescope system stands on two volcanic peaks in Hawaii, scanning the sky every night with patient, tireless attention. Atlas doesn't look for beauty or meaning. It simply watches for anything that moves, anything that changes, anything that appears where darkness used to be. On that late December night in 2019, it found something. A tiny point of light magnitude 19.6, so faint, you'd need a telescope just to prove it existed. The astronomers cataloged it with a careful bureaucratic name, C2019Y4. The C meant comet, the numbers meant the year and the half month of discovery. The Y4 meant it was the fourth such object found in that particular slice of December. But names like that rarely capture what something truly is. As the nights passed and more observations accumulated, something unusual began to emerge from the data. This comet was moving fast, really fast, with a velocity that made astronomers lean closer to their screens. When you track an object's path backward through space, you can usually trace it to some distant corner of our solar system. The Oort cloud, perhaps that vast sphere of icy bodies surrounding our sun like a cosmic snow globe, extending nearly halfway to the nearest star. Most comets come from there, shaken loose by gravitational nudges, falling inward on journeys that take millions of years. But Atlas seemed different. Its trajectory bent in a way that whispered of elsewhere. Scientists suggest that when a comet's orbit is open rather than elliptical, when the numbers describing its path lean towards something called hyperbolic, it might not be bound to our sun at all. It might be just passing through a traveler on a road that began somewhere we've never seen. Imagine that for a moment. Throughout all of human history, every comet we've ever observed, from the omen that terrified ancient civilizations to Halley's clockwork return every 76 years, has belonged to our solar system. They're our cosmic neighbors, members of the sun's extended family, even if they only visit the inner solar system once every few millennia. But an interstellar comet one, born in orbit around another star perhaps hundreds or thousands of light years away, that would be something else entirely. A message in a bottle thrown across the ocean of space itself. The excitement in the astronomical community was quiet but electric. Just months earlier, in August 2019, astronomers had confirmed only the second interstellar object ever identified, a comet called 2I Borisov. The first, the mysterious cigar-shaped Oumuamua in 2017, had sparked debates that continue even now. Was it a comet, an asteroid, something else? Borisov was definitely a comet, sporting a beautiful tail of gas and dust, and its chemistry matched nothing in our solar system. It was a visitor unmistakably foreign. Now, here was Atlas, possibly a third interstellar wanderer in just a few years. Could it be that our solar system passes through these cosmic travelers more often than we ever realized? That the space between stars isn't as empty as we once imagined, but instead filled with orphaned worlds, ejected planets, rogue comets, all silently drifting through the dark. Research shows that when a planetary system forms, chaos reigns for millions of years. Planets migrate, throwing smaller bodies into wild orbits or slinging them out into interstellar space entirely. Computer models suggest that for every planet that finds a stable orbit, hundreds or thousands of comets and asteroids are ejected sent, wandering into the galaxy with no home to return to. If every star system does this, then interstellar space becomes a slow river of exiles flowing between the stars. Atlas might be one of those exiles. Born perhaps around a star we'll never know, in a solar system that formed its own story billions of years ago. Ejected by the gravitational dance of forming planets, it would have drifted for eons through the cold and dark until by chance, by pure statistical inevitability, it wandered close to our sun. The early observations showed something else remarkable. Atlas was big, not just a small icy boulder, but a substantial nucleus estimated at several kilometers across. Research shows that when a comet gets closer to the sun, warmth begins to vaporize the ice on its surface. Water sublimates directly from solid to gas, carrying dust particles with it, creating a glowing atmosphere called a coma that can grow larger than Jupiter itself. Atlas was still far from the sun in those first observations, way out beyond Mars, but it was already showing signs of activity. And then the predictions began. Scientists plotted Atlas's trajectory forward, calculating where it would be in the coming months. The orbit would bring it remarkably close to the sun, a mere 23 million miles from our star's surface, closer than the orbit of Mercury. At that distance, the solar radiation would be intense, heating the comet's nucleus, triggering violent outgassing. Some comets survive such an encounter, some don't. But if Atlas held together, if it weathered the approach, the calculations suggested something spectacular. Magnitude predictions soared upward. By early May 2020, Atlas might become magnitude 10 or brighter. To put that in perspective, the full moon shines at magnitude 12.6. The brightest stars in our sky barely reach magnitude 1.5. A magnitude 10 comet would be visible in broad daylight, a brilliant smudge against the blue sky outshining everything except the sun and moon themselves. It would be the comet of a lifetime, visible to anyone who simply looked up. The brightest comet in recorded history, brighter than Comet McNaught in 2007, brighter than Hale-Bopp in 1997, brighter than the Great Comet of 1811 that inspired Tolstoy's prose in War and Peace. Excitement rippled through both professional and amateur astronomy communities. Observation campaigns were planned, telescopes were scheduled. Even in the midst of a world beginning to grapple with a pandemic, there was something beautiful about the timing, a celestial wonder arriving just when humanity needed a reminder that the universe still held marvels, still offered gifts of light in dark times. But comets keep their own counsel. They're ancient, fragile things held together by ice and gravity and time. They have survived in the deep freeze of space for billions of years, but the warmth of the inner solar system is a test many fail. Atlas was speeding toward that test, and the world watched hoping. Do you ever wonder what it would be like to see something no generation has seen before? To look up and know that the light touching your eyes traveled from ice born around another star. Throughout January and February 2020, Atlas brightened steadily right on schedule. It was still faint to the naked eye, but telescopes showed it growing more active, its coma expanding, its tail lengthening. Everything seemed to be proceeding exactly as predicted. But space has a way of reminding us that predictions are just educated guesses, and comets are among the most unpredictable objects in the solar system. In early March, something changed. The brightening slowed, then it stopped. Images taken on March 11th showed the comet's nucleus had split. Then, it split again. And again. Atlas was falling apart. The comet that had promised to light up the spring sky that might have become the brightest in human history was crumbling into fragments even as it raced toward the sun. Each piece would be smaller, weaker, less able to produce the spectacular display that had been forecast. The cosmic visitor that might have told us stories about alien solar systems was dissolving before our eyes, returning to the dust from which it came. Scientists suggest that comet nuclei are often described as rubble piles, loose collections of ice and rock held together more by weak gravity than structural strength. When the sun's heat reaches the interior, pressure builds, gases expand, fractures widen. Sometimes a comet can hold together through this stress. Sometimes it cannot. Atlas could not. But even in its destruction, even in what might seem like cosmic disappointment, Atlas still had secrets to share. The fragments continued inward, each one now a separate target for observation. Each one offering astronomers a rare chance to see not just a comet's surface, but its interior structure. The pristine material that had remained frozen and unchanged since the comet's formation billions of years ago. What stories did those fragments tell? What did their chemistry reveal about the place they were born? And if Atlas truly was an interstellar visitor, what could its composition teach us about solar systems beyond our own? The mystery of Atlas was just beginning. The visitor from the dark was about to reveal its secrets one glowing fragment at a time. To understand what Atlas truly was, we need to look closer at the architecture of these frozen wanderers, at the delicate construction that allows them to survive billions of years in the void, only to come apart in warmth and light. Every comet is a time capsule, but not all capsules are built the same. The nucleus, the solid heart of a comet, is where everything begins. For Atlas, early estimates suggested a nucleus somewhere between 3 and 5 kilometers across, roughly the size of a small mountain drifting through space. That might sound modest compared to planets or moons, but in the world of comets, size matters in unexpected ways. A nucleus that large carries tremendous mass, tremendous inertia, and when heated by the sun, tremendous energy waiting to be released. Scientists suggest the nucleus of a comet is composed primarily of water ice, but not the clear crystalline ice you might find in a winter stream. This is ancient ice formed in temperatures near absolute zero, mixed intimately with dust particles, rocky grains, and frozen gases that exist only in the deepest cold of space. Carbon dioxide ice frozen harder than steel, methane ice preserved for eons. Carbon monoxide, ammonia, formaldehyde, all locked in a matrix so cold that molecular motion nearly stops. Research shows that when astronomers analyze the light reflected from a comet's surface, they can identify these components by their spectral fingerprints. Each molecule absorbs and reflects specific wavelengths, creating a pattern as unique as a barcode. Water shows up clearly in infrared wavelengths. Carbon dioxide leaves its signature in ultraviolet. By carefully measuring these patterns, scientists can essentially read the chemical composition of an object millions of miles away, never touching it, never collecting a sample, simply listening to the story light tells. For Atlas, early spectroscopic observations revealed something fascinating. The ratio of certain isotopes, the balance between different forms of water molecules, suggested ice that formed in extremely cold conditions, colder even than the current temperature of the Oort cloud. Some researchers propose this might indicate a formation region far from any star in the frozen depths between solar systems. Others suggested it could have formed in the outer reaches of a distant planetary system, beyond where even Neptune-like planets orbit. The debate illustrates a beautiful uncertainty in astronomy. We can measure, we can analyze, but interpretation requires careful humility. The same data can tell different stories, depending on which assumptions you begin with. But the nucleus is only the beginning of a comet's anatomy. As Atlas approached the sun through January and February 2020, solar radiation began its patient work. Photons traveling 93 million miles from the sun's surface struck the dark, dusty ice of the nucleus. That energy absorbed by the surface converted to heat. And ice, even ancient ice, eventually responds to warmth. Sublimation is a strange and beautiful process. The ice doesn't melt, there's no liquid phase in the vacuum of space. Instead, solid transforms directly to gas-water molecules, breaking free from the crystal lattice and streaming outward into the void. Each escaping molecule carries dust particles with it, grains that had been frozen in place for billions of years, suddenly liberated, catching sunlight, beginning to glow. This expanding cloud of gas and dust is called the coma, and it can grow to astonishing sizes. Research shows that while the nucleus might be just a few kilometers across, the coma can swell to over 100,000 kilometers in diameter, larger than Jupiter, the largest planet in our solar system. Imagine that scale. A mountain-sized object creating an atmosphere bigger than a gas giant. It's one of the most dramatic transformations in nature, a tiny seed of ice blossoming into something that dominates the sky. Atlas's coma grew steadily through late January and early February. Observations from multiple telescopes showed it expanding, brightening the dust production, increasing as more surface area became active. The color of the coma revealed more chemistry. A greenish tint suggested diatomic carbon C2, a molecule that forms when sunlight breaks apart larger organic compounds in the comet's ice. A bluish component indicated ionized carbon monoxide CO+, created when ultraviolet radiation strips electrons from CO molecules. Each color, each wavelength, each spectral line added another piece to the puzzle of what Atlas was made of and where it might have formed. The tail is perhaps the most iconic feature of a comet, the element that has inspired fear and wonder throughout human history. But here's something that surprises many people. Most comets actually have two tails, not one, and they point in different directions. The dust tail forms from those particles liberated by sublimating ice. These grains are tiny, often smaller than particles of talcum powder, but they're solid, they have mass, and they respond to forces differently than gas. As they stream away from the nucleus, they follow curved paths shaped by the comet's motion through space and by a subtle pressure called radiation pressure, where photons from the sun literally push on the dust grains, slowly accelerating them outward. The dust tail curves gently tracing the comet's path, often appearing yellowish or white, because it simply reflects sunlight. The ion tail is something else entirely. This is gas molecules that have been ionized by solar ultraviolet radiation, stripped of electrons, and left electrically charged. These ions respond not to radiation pressure, but to the solar wind, that constant stream of charged particles flowing outward from the sun at 1,000,000 miles per hour. The solar wind carries a magnetic field with it, and ionized molecules in the coma get caught in that field, dragged along, streaming directly away from the sun in a perfectly straight line, regardless of the comet's direction of motion. For Atlas, both tails were developing beautifully by late February. Images showed the characteristic fan-shaped dust tail and a narrower, straighter ion tail, glowing with a bluish tint from ionized molecules. The ion tail stretched for millions of kilometers, a ghostly streamer pointing away from the sun like a cosmic windsock. But there was a third component to Atlas's structure, one that became tragically important. Deep within the nucleus, beneath layers of ice and dust, stresses were building. Research shows that comet nuclei are often highly fractured, full of cracks and voids, not solid blocks, but more like loosely packed snowballs, what planetary scientists call rubble piles. The individual components might be bound together by ice acting as cement, but that bond is only as strong as the ice itself. As the outer layers sublimated away, as gases formed in pockets within the nucleus, pressure increased. Some comets have strong enough internal structure to contain this pressure. Others develop weak points, fracture lines, where stress concentrates. For Atlas, those fracture lines prove fatal. The nucleus composition likely included volatile ices beyond just water. Carbon monoxide, which sublimates at much lower temperatures than water, might have been vaporizing deep within the nucleus, creating gas pressure in enclosed pockets. When that pressure exceeded the strength of the surrounding ice, fractures would propagate, weakening the structure, making the next fracture easier, creating a cascade of destruction. Think of it like this. Imagine a frozen lake in early spring. The ice might look solid, might be thick enough to walk on, but beneath the surface, warmth is doing invisible work. Water is melting in tiny channels, weakening bonds between ice crystals. Then one day, seemingly without warning, the ice gives way. Not because anything dramatic happened in that moment, but because the accumulated stress finally exceeded what the structure could bear. Atlas experienced something similar, but on a cosmic scale. By March 11, 2020, observations showed the nucleus had broken into at least 2 pieces. By March 20th, those pieces had broken further, creating a string of at least 4 separate fragments. By early April, the fragmentation had become so extensive that the original nucleus no longer existed as a single object. What had been a mountain of ice was now a scattered cloud of smaller pieces, each following nearly the same orbit, each slowly drifting apart. The predicted magnitude, 10 spectacle, evaporated with the ice. Each fragment was smaller, produced less gas, reflected less light. Instead of one brilliant comet dominating the sky, there would be nothing visible to the naked eye at all. For many, it felt like a cosmic disappointment, a promise broken. But for scientists, this was a gift of a different kind. The fragments of Atlas offered something rarely seen, a view of a comet's interior structure, the pristine material that had been shielded from solar radiation and cosmic rays for billions of years. Each fragment became a separate laboratory, a chance to study composition and behavior at scales impossible for an intact nucleus. What was Atlas truly made of? The answer lay scattered across millions of kilometers of space, glowing, softly dying, slowly, but still whispering secrets to anyone patient enough to listen. And those whispers would tell a story about origins, about the fundamental question that made Atlas so compelling in the first place. Where did this wanderer truly come from? The question of origin is perhaps the most profound we can ask about anything drifting through space. Where something was born shapes everything about what it becomes, the chemistry locked in its ice, the structure of its interior, even the trajectory that eventually brings it near our sun. For Atlas, that question carried unusual weight, because the answer might reshape how we understand the space between stars. When astronomers first calculated Atlas's orbit with precision, they noticed something that made conversations pause, that made researchers lean back in their chairs and stare at their screens a little longer. The orbital eccentricity, a number that describes how elliptical or open a trajectory, is measured very close to 1.0. In orbital mechanics, an eccentricity of exactly 1.0 means a parabolic orbit, the boundary between closed and open, between bound and free. Anything above 1. O is hyperbolic, an orbit that never closes a path, that leads away from the sun and never returns. Atlas's eccentricity hovered right at that boundary, maybe slightly above, maybe slightly below, the uncertainty in the measurement straddling the line between 2 fundamentally different fates. If it was truly hyperbolic, if the orbit was genuinely open, then Atlas wasn't bound to our sun. It had come from somewhere else, and would eventually return to somewhere else, passing through our solar system just once in all of cosmic time. But here's where orbital mechanics becomes beautifully complicated. Research shows that even comets from the Oort cloud, firmly part of our solar system, can have orbits that appear nearly parabolic when they first enter the inner solar system. They've been traveling for millions of years from distances so vast that their connection to the sun is gravitationally tenuous, a whisper of attraction across trillions of miles. Their orbital energy balance is right at the edge of escape velocity, appearing almost indistinguishable from truly interstellar objects. The distinction requires exquisitely precise measurements. You need to know not just where the comet is, but exactly how fast it's moving, and in precisely which direction. You need to account for the gravitational influence of every planet. It passes the subtle non-gravitational forces created by outgassing jets on the nucleus surface. Even the pressure of sunlight itself, pushing gently on the comet's coma and tail. Small errors in any of these measurements can flip the determination from bound to unbound, from solar system native to interstellar visitor. For Atlas, the early orbital calculations suggested ambiguity. Some solutions came out hyperbolic, implying interstellar origin. Others, accounting for observational uncertainties differently, showed an extremely long period elliptical orbit, perhaps 6,000 years or longer, originating from the Oort cloud, but still gravitationally tied to our sun. The fragmentation of the nucleus in March complicated matters further, because outgassing from the breaking pieces created non-gravitational accelerations difficult to model accurately. This uncertainty echoes a pattern that has played out before in astronomical history. In October 2017, the Pan-STARRS telescope in Hawaii detected an object moving through the inner solar system at extraordinary speed. Initially cataloged as a comet, then reclassified as an asteroid, it received the designation One Eyes Oumuamua, the first confirmed interstellar object ever observed passing through our solar system. The one eye meant first interstellar, a new classification created specifically for this discovery. Oumuamua's orbit was unambiguously hyperbolic eccentricity, well above 1, moving far too fast to be bound to the sun. But almost everything else about it sparked debate that continues even now. Its shape appeared highly elongated, perhaps 10 times longer than it was wide, unlike any asteroid or comet nucleus previously observed. It showed no visible coma, no tail, no clear signs of outgassing, yet its trajectory indicated a small, non-gravitational acceleration, as if something was gently pushing it. Some scientists proposed it was a nitrogen iceberg, a fragment broken from a Pluto-like world in another solar system. Others suggested it was ordinary water ice with an unusual insulating crust that prevented visible outgassing. A few researchers more speculatively wondered if it could be something artificial. A light sail perhaps, though this idea remained highly controversial and lacked supporting evidence. The point is this: even with an unambiguous interstellar trajectory, even with months of observations from the world's best telescopes, fundamental questions about Oumuamua's nature and composition remain unsettled. The universe doesn't always provide clear answers, even when we ask carefully. Then came 2I Borisov in August 2018, discovered by amateur astronomer Gennady Borisov using a telescope he built himself. Borisov's orbit was also clearly hyperbolic, but unlike Oumuamua, this object behaved exactly like a comet. It developed a beautiful coma, sprouted prominent tails, showed spectroscopic signatures of water, carbon monoxide, and cyanide, outgassing all the chemistry expected from a typical comet nucleus. But typical only describes behavior, not origin. When astronomers analyzed the gas production rates and composition ratios, they found something intriguing. The ratio of carbon monoxide to water was much higher in Borisov than in solar system comets, perhaps 3 to 10 times higher, depending on which measurements you trusted. This suggested formation in a particularly cold environment, colder than the conditions where solar system comets formed. Some researchers interpreted this as strong evidence that Borisov formed in the outer regions of its birth system, perhaps beyond where Pluto-like objects orbit in our own system. The higher CO content would make sense if the comet accreted in temperatures cold enough to trap even the most volatile gases efficiently. It was chemistry that whispered of alien cold of distances and darkness our own solar system's architecture can barely imagine. Atlas, discovered just months after Borisov's apparition, naturally invited comparison. Both were large comets, both showed strong activity far from the sun, both had orbital characteristics suggesting possible interstellar origin. But there were differences too. Atlas's composition, as measured from early spectroscopy, showed a more typical ratio of gases closer to what we see in Oort cloud comets. The nucleus appeared less cohesive, breaking apart well before reaching perihelion, whereas Borisov survived its closest approach to the Sun intact. These differences mattered because they hinted at different formation histories. If Atlas truly came from another star system, it might have formed in conditions more similar to our own Oort cloud in a solar system, with similar architecture, similar planet masses, similar distances defining the snowline where ices could condense. Or perhaps it formed in our own solar system, but was perturbed into an orbit so extreme that it mimicked interstellar characteristics. Scientists suggest that calculating an object's origin with certainty requires tracing its trajectory not just within our solar system, but backward through interstellar space, accounting for the sun's motion through the galaxy. The gravitational influence of nearby stars, even the tidal forces of the Milky Way's galactic disk. For objects moving at interstellar velocities, this becomes a problem of galactic dynamics, requiring knowledge of stellar positions and velocities going back millions of years. For Atlas, such calculations remained inconclusive. The fragmentation made precise trajectory determination difficult. The earliest observations before astronomers realized its importance were sparse. Unlike Oumuamua and Borisov, which had been tracked intensively from discovery, Atlas broke apart before its nature could be firmly established. It became a question mark, maybe a cosmic, we'll never know for certain. But perhaps there's something appropriate about that uncertainty. The space between stars is vast beyond human comprehension. Distances measured in light years and trillions upon trillions of miles. Objects drifting through that space carry no labels, no identification tags marking their birth system. They're orphans of gravitational chaos, ejected from their homes by processes that happened billions of years ago, long before Earth existed. Long before our sun had finished gathering its family of planets. Research shows that every star system probably loses far more material than it keeps. During planet formation, the gravitational interactions are violent and indiscriminate. Jupiter-sized planets migrate inward, scattering smaller bodies like cosmic billiard balls. Close encounters between forming planets can eject entire protoplanets into interstellar space. The process is inefficient, messy, creative in its destruction. If you could somehow count all the objects in interstellar space, all the orphaned comets and asteroids drifting between the stars, the number would be staggering. Some estimates suggest there could be quadrillions of such objects in our galaxy alone, far outnumbering the comets and asteroids that remain bound to their parent stars. Interstellar space isn't empty. It's full of exiles, wanderers, fragments of worlds that might have been. Atlas might be one of those exiles, born perhaps 5 billion years ago around a star whose light has never reached Earth in a planetary system that followed its own story, developed its own worlds, maybe even its own life. Ejected in the chaos of formation, it would have drifted for eons, cooling gradually, its surface darkened by cosmic ray impacts, its interior remaining pristine and frozen. A message written in ice that no one could read, until by pure chance, its path intersected ours. The odds of such an intersection are vanishingly small for any single object, but with quadrillions of wanderers and billions of star systems, statistical inevitability takes over. Some must pass through. Some must come close enough to be seen. And when they do, when these visitors from the dark arrive in our sky, they carry questions we're only beginning to learn how to ask. Questions about the diversity of planetary systems, about the conditions in which planets form, about whether the chemistry of life might be scattered throughout the galaxy in these frozen libraries drifting through the void. Atlas fragmented before giving final answers, but the pieces continued forward, each one still holding secrets, still carrying that fundamental mystery in their ice. The question of where Atlas came from would eventually shift to a related question equally profound. What was it made of, and what could that composition reveal about its birthplace wherever and whenever that might have been? There's something poignant about a promise the universe makes and then quietly takes back, about expectations built on mathematics and shattered by physics about the difference between what we calculate and what actually unfolds in the cold machinery of space. In January 2020, as Atlas brightened steadily in telescopes around the world, the predictions grew bolder with each passing week. Astronomers plugged observational data into their models, extrapolating forward based on how comets typically behave as they approach the sun. The mathematics was elegant, the physics well understood. If Atlas continued its current rate of brightening, if its nucleus remained intact, if the outgassing increased according to standard models, then by early May something extraordinary would happen. The comet would become visible in broad daylight, a celestial beacon bright enough to cast shadows, potentially the most spectacular comet in recorded history. Magnitude predictions climbed toward 10 or even 11 numbers that put Atlas in a category shared by almost nothing except the sun and moon. Social media buzzed with anticipation. Astronomy forums filled with discussions about optimal viewing times, camera settings for astrophotography, plans for observation parties. Even mainstream news outlets began preparing stories about the coming celestial show. In a world suddenly thrust into lockdowns and uncertainty due to a global pandemic, the promise of Atlas felt like a gift, a reminder that the cosmos still held wonder, still offered moments of shared awe that transcended borders and circumstances. But comets are not known for keeping promises. They're known for defying them. The first hints of trouble appeared in early March, subtle at first, easy to dismiss as observational noise or atmospheric distortion. The rate of brightening began to slow, not dramatically, but enough that careful observers noticed. Light curves graphs plotting the comet's brightness over time showed a flattening where the slope should have continued climbing steeply upward. Some astronomers suggested this might be temporary, perhaps a lull in activity before a new surge, a common enough pattern in the cometary behavior. Then on March 11th, high-resolution images from the Hubble Space Telescope revealed something that changed everything. The nucleus wasn't a single point of light anymore. It had elongated, stretched, split into at least two distinct fragments separated by a growing distance. Atlas was coming apart. Research shows that cometary fragmentation is not uncommon, but it's also not fully understood. The mechanisms that hold a comet nucleus together are complex. A balance between gravitational self-attraction, tensile strength of ice acting as cement between dust grains, and internal pressure from sublimating volatiles. When this balance tips, when stress exceeds strength, the nucleus fractures. But predicting exactly when and how this will happen remains an inexact science, more art than equation. For Atlas, the fragmentation accelerated rapidly. By March 20th, observations showed at least 4 separate fragments, each producing its own small coma, each drifting slowly away from the others. By early April, the fragmentation had become so extensive that the original nucleus structure was essentially gone, replaced by a scattered cloud of dozens, perhaps hundreds of smaller pieces, each following nearly the same orbit, but spreading out along the trajectory like beads on a cosmic string. Each fragment was smaller, contained less mass, less ice, produced less gas and dust when heated by the sun. The combined brightness of all the fragments together never approached what the intact nucleus would have produced. Instead of magnitude, 10 Atlas peaked around magnitude 8, faint enough that you'd need binoculars or a small telescope just to glimpse it. The daytime spectacle evaporated as surely as the comet's ice. Have you ever built something in your mind, imagined it so clearly that it felt almost real, only to watch circumstances quietly dismantle those plans piece by piece? That's what the astronomical community experienced with Atlas, a collective deflation of hope, though tempered by scientific curiosity about what the fragmentation might reveal. The story of Atlas's destruction echoes other cometary disappointments throughout history, each one a reminder that nature doesn't perform on schedule, doesn't respect human expectations. In 2013, Comet Ison was discovered on a trajectory that would bring it extremely close to the Sun, just 730,000 miles from the solar surface. Predictions suggested it might become the comet of the century, visible even in daylight as it rounded the Sun on Thanksgiving Day 2013. Millions of people planned to watch. Media coverage intensified as the comet approached. On November 28th, Ison plunged toward the Sun, and telescopes worldwide turned their attention to the spectacle. For a few hours, Ison brightened dramatically as solar radiation vaporized its surface at an astonishing rate, but the nucleus subjected to temperatures exceeding 5,000 degrees Fahrenheit. And tidal forces strong enough to tear mountains apart couldn't withstand the stress. Ison emerged from its closest approach as little more than a diffuse cloud of dust, the nucleus completely destroyed. Within days, even that dust had dispersed, becoming invisible. The comet of the century left behind no legacy in the sky, just data observations lessons about fragility and the limits of prediction. In 2000, Comet Linear. Another object that had sparked excitement with early brightness predictions, also fragmented as it approached the Sun. Observations showed the nucleus breaking into more than a dozen pieces, each piece subsequently breaking further, creating a hierarchy of destruction that astronomers watched in real time. Linear never became the naked eye spectacle anticipated. Instead, it provided a masterclass in how comet nuclei can fail the various ways that structure and strength can give way under thermal and gravitational stress. Scientists suggest that the key factor in cometary fragmentation is often the internal structure of the nucleus. The rubble pile model proposes that many comet nuclei aren't monolithic blocks of ice, but rather loose aggregations of smaller chunks, held together by a combination of gravity and ice that acts like weak mortar between bricks. Such structures can survive billions of years in the deep freeze of the Oort cloud, or interstellar space where temperatures hover just a few degrees above absolute zero. And nothing changes, nothing stresses, nothing moves. But approaching the Sun changes everything. Solar radiation heats the surface unevenly, creating temperature gradients, thermal expansion, stress fractures. Volatiles trapped within the nucleus sublimate building pressure in enclosed pockets. If there are pre-existing cracks or weak layers in the structure, these become failure points where the nucleus can split. The rotation of the nucleus adds another layer of complexity. Most comets rotate sometimes slowly, sometimes rapidly, completing one turn in hours or even minutes. This rotation creates centrifugal forces that pull outward, fighting against the weak gravity trying to hold the nucleus together. For small bodies, objects just a few kilometers across, gravity is feeble. It doesn't take much additional force to overcome it. Research shows that jets of sublimating gas can also create asymmetric forces on different parts of the nucleus, torquing it, spinning it up, creating stresses that accumulate over time. A comet approaching the Sun for the first time coming in from the Oort cloud or from interstellar space experiences thermal stress it has never felt before. The ice has never been warm, never sublimated at these rates, never produced these pressures. The structure is being tested in ways it wasn't designed to handle, if designed is even the right word for something assembled by random collision and gentle accumulation in the cold, dark billions of years ago. For Atlas, the specific mechanism of fragmentation remains uncertain. Some researchers propose that the nucleus might have had a particularly high content of volatile ices like carbon monoxide or methane, which sublimate at lower temperatures than water ice. As these volatiles vaporize deep within the nucleus, they could have created internal pressure that fractured the structure from the inside out, like a bottle of frozen soda expanding as it thaws. Others suggested that Atlas might have been a particularly loose rubble pile, held together so weakly that even modest thermal stress was enough to pull it apart. The relatively large size of the nucleus several kilometers across would mean gravity was slightly stronger than for smaller comets, but perhaps not strong enough to compensate for structural weakness. There's also the possibility that Atlas experienced a collision at some point in its past, either in its birth system or during its journey through interstellar space. Even a small impact could create internal fractures, hidden damage that wouldn't be apparent from surface observations, but would weaken the overall structure, creating failure points that would only manifest under stress. One of the common mistakes in predicting comet brightness is assuming structural integrity. The mathematical models that extrapolate brightness forward typically assume the nucleus will remain intact, that the outgassing will increase smoothly as solar heating intensifies, that nothing catastrophic will happen. It's a reasonable assumption for most comets, particularly those on short-period orbits that have survived multiple passes near the Sun, demonstrating their resilience. But for new comets objects making their first approach or potentially interstellar visitors like Atlas, there's no track record, no history of survival to provide confidence. The lesson Atlas teaches is one of humility. Even with sophisticated observatories, decades of experience, mathematical models refined by hundreds of previous comets, we still cannot predict with certainty what will happen when ice meets fire, when ancient structure confronts modern stress. The universe retains its capacity to surprise, to disappoint, to remind us that observation is not the same as understanding. But disappointment is a human emotion, and it comes from expectations from hopes built on predictions that turned out to be wrong. The universe itself feels nothing about Atlas fragmenting. The comet followed physical laws, perfectly responding exactly as it must to the forces acting upon it. The fragmentation wasn't a failure, except in relation to human hopes for a spectacular show. And in a different sense, Atlas's destruction was itself spectacular, just not in the way anyone anticipated. The process of watching a mountain-sized object fall apart across millions of miles of space, tracking each fragment as it pursued its own small trajectory, analyzing the composition of material that had been hidden inside the nucleus for billions of years. All of this was scientifically extraordinary, even if it wasn't visually stunning to casual observers. The fragments continued inward, each one now a separate target for observation, each one revealing its secrets in the light it reflected and the gases it released. The story wasn't over. In some ways, it was just beginning, because now astronomers had access to something precious and rare, a view beneath the surface, a chance to see what comets hide in their frozen hearts. Sometimes destruction is just another form of revelation, a way for hidden things to become visible, for secrets kept in darkness to finally meet the light. When Atlas broke apart across those weeks in March and April 2020, it opened itself in ways an intact nucleus never could. Each fragment became a window into the interior, exposing material that had been shielded from cosmic radiation and solar heat for billions of years. Material that still carried the chemical fingerprint of wherever and whenever the comet formed. The fragmentation transformed disappointment into opportunity, turned a visual spectacle that never happened into a scientific treasure that did. The Hubble Space Telescope became the primary witness to Atlas's dissolution. Hubble's position above Earth's atmosphere gives it a clarity that ground-based telescopes cannot match. No distortion from air currents, no interference from weather or city lights. On April 20th and April 23rd, 2020, Hubble captured detailed images of the fragmenting nucleus, revealing approximately 25 distinct pieces, each one drifting slowly away from the others, each one surrounded by its own small coma of sublimating gas and dust. These images were more than just pictures. They were data encoded in light wavelengths, carrying information about composition in temperature, particle size, gas production rates. Scientists suggest that by analyzing the brightness and color of each fragment, by measuring how quickly they separated and how their individual comas evolved, researchers could infer properties of the parent nucleus that would have remained hidden if the comet had stayed intact. One of the most striking revelations was about the nucleus structure itself. The fact that Atlas broke into so many pieces and that those pieces continued to break further over subsequent weeks strongly supported the rubble pile model, rather than the idea of a monolithic solid nucleus. Research shows that a solid block of ice would be much more likely to crack into 2 or 3 large pieces. The fragmentation of Atlas into dozens of fragments suggested a structure more like a loosely packed snowball. Many individual components weakly bound together, coming apart when the binding weakened. The size distribution of the fragments also told a story. The largest pieces were estimated at a few hundred meters across, far smaller than the original nucleus. But there were many more small fragments than large ones, following a pattern consistent with hierarchical breakup, where large pieces split into medium pieces, which split into small pieces, which split into dust. This cascade of destruction implied that there was no strong core holding everything together, no dense central region that remained intact. The entire structure was fragile, pervasively weak. Spectroscopic observations of the fragments provided chemical insights impossible to obtain from an intact nucleus. When you observe a comet with its nucleus intact, the spectroscopy primarily samples the outermost surface layers, the material directly exposed to sunlight. But the interior might be different, protected from solar radiation, perhaps enriched in more volatile ices that would have sublimated away from the surface during previous warm periods if the comet had ever been near a star before. The fragments exposed that interior material. As each piece broke away, fresh surfaces appeared, surfaces that had been deep inside the nucleus just days or weeks earlier. The gases sublimating from these fresh surfaces carried their own chemical signatures, revealing ratios of molecules that differed subtly from what had been observed before the fragmentation. One particularly interesting finding involved the ratio of carbon monoxide to water. Early observations of intact Atlas showed a relatively standard ratio similar to many Oort cloud comets. But as fragments broke off and exposed interior material, some showed enhanced carbon monoxide, suggesting that CO was more abundant in the interior than on the surface. This makes sense from a physics perspective. Carbon monoxide ice sublimates at much lower temperatures than water ice, around -205 degrees Celsius, compared to water sublimation near -100 degrees Celsius in vacuum. In the frigid environment of interstellar space or the distant Oort cloud, both would be stable. But if Atlas had ever experienced even mild warming, perhaps, from passing near a star other than our sun, or from heat generated by radioactive decay in its interior, the carbon monoxide on the surface would have sublimated, first escaping into space, leaving the surface enriched in water ice while CO remained trapped deeper inside. The fragmentation exposed that trapped CO, allowing it to sublimate for the first time in billions of years. There's something almost poetic about that. Don't you think gases frozen since before Earth existed suddenly released, expanding into space, catching sunlight, revealing their presence through the specific wavelengths they absorb and emit? Ancient chemistry finally readable. The dust released by the fragments also carried information. Research shows that when cometary dust is analyzed spectroscopically, it reveals the presence of silicate minerals, organic compounds, sometimes even complex carbon molecules, called polycyclic aromatic hydrocarbons, or PAHs. These molecules are interesting because they're associated with star-forming regions, with the interstellar medium itself, the diffuse gas and dust between stars where new solar systems are born. For Atlas dust analysis showed the presence of silicates consistent with olivine and pyroxene minerals, common in rocky bodies throughout the solar system, and presumably throughout the universe wherever planets form from similar materials. The organic component was harder to characterize precisely, but spectral features suggested the presence of carbon-rich compounds, possibly including simple organic molecules like formaldehyde methanol and ethane. These compounds are interesting because they are considered prebiotics, not life itself, but the chemical building blocks from which biological molecules might eventually form. The discovery of such compounds in comets has led to the hypothesis supported by considerable evidence that comets may have played a crucial role in delivering organic chemistry to the early Earth. Billions of years ago, when our planet was young and still being bombarded by debris left over from solar system formation, comets would have struck the surface frequently, bringing not just water, but also the chemical ingredients necessary for life. If Atlas truly was an interstellar comet, if it formed around another star, the presence of these organic compounds would suggest that the chemistry of life's precursors might be universal, not unique to our solar system. That wherever planets form, wherever comets accumulate in the cold outer reaches of solar systems, the same basic chemical processes produce the same kinds of molecules. It's a humbling thought that the chemistry happening inside you, the molecules enabling your consciousness, might be assembled from ingredients common throughout the galaxy, delivered by visitors from the dark. The rate at which fragments separated provided another insight. By measuring the positions of fragments over multiple days and calculating their velocities, researchers could estimate how much energy was involved in the breakup. The speeds were slow, typically just a few meters per second, about walking pace. This tells us that the fragmentation wasn't explosive, wasn't driven by sudden violent outgassing. Instead, it was gentle, almost leisurely, the nucleus simply falling apart as the weak bonds holding it together failed one by one. Compare this to some other fragmentation events observed in cometary history. In July 1994, comet Shoemaker-Levy 9 had already been torn apart by Jupiter's gravity 2 years earlier, and the fragments were stretched into a chain that spectacularly impacted Jupiter's atmosphere, creating massive explosions visible even in amateur telescopes. That fragmentation was violent, driven by tidal forces so strong they ripped the nucleus apart in hours. Atlas's fragmentation was nothing like that. It was slow, almost passive, a structure simply surrendering to stresses it couldn't withstand. The gentleness of the process actually makes it more informative in some ways, because it reveals the intrinsic weakness of the structure, rather than the overwhelming power of external forces. Ground-based telescopes around the world also contributed observations. The Las Cumbres Observatory Network, a global array of robotic telescopes, tracked Atlas fragments across multiple sites, ensuring continuous coverage as Earth rotated. Amateur astronomers with backyard telescopes contributed observations, part of a distributed network of sky watchers who collectively provide coverage that no single professional observatory could match. This collaborative approach to observation is one of astronomy's great strengths. Professional researchers define the targets and coordinate the observations, but the actual data comes from dozens or hundreds of separate telescopes, each contributing a few data points that, when combined, create a complete picture no single observer could capture alone. For Atlas, this distributed observation network tracked fragments for weeks, documenting their continued fragmentation, their gradually diminishing brightness, their slow dispersal along the orbital path. By late April and early May 2020, when Atlas should have been dominating the sky at magnitude 10, the fragments had faded to magnitude 11, or dimmer and visible to all but the largest amateur telescopes and professional instruments. The show that never happened had been replaced by a quieter spectacle visible only to those with the tools and patience to seek it out. But the scientific value remained high. Each observation added to the data set. Each spectrum contributed another piece to the puzzle of what Atlas was made of and how its nucleus was structured. The fragmentation had transformed one large mystery into dozens of smaller mysteries, each fragment a separate question about composition, each trajectory a separate clue about structural strength and internal forces. One lesson that emerged clearly from Atlas's fragmentation: is that predicting comet behavior requires more than just mathematical models of brightness and orbital mechanics. It requires understanding material science at the most extreme conditions, ice mechanics at temperatures where molecular motion nearly stops structural engineering for objects held together by gravity so weak that thermal expansion can overcome it. We often think of space as a realm of vast forces of black holes and supernovae of gravity strong enough to warp space-time itself. But in the realm of small bodies of comets and asteroids, the relevant forces are tiny, subtle, barely strong enough to hold dust grains together. A comet nucleus several kilometers across might have surface gravity less than 1/10,000th of Earth's gravity. On such an object, you could jump and simply drift away into space. The cohesion that keeps the nucleus intact is barely stronger than the adhesion of frost on a window. Understanding how such structures respond to stress, how they fail, what patterns emerge during fragmentation. These questions require careful observation of events like Atlas's breakup. Each fragmentation is unique, driven by the specific structure and composition of that particular nucleus, but patterns emerge across multiple observations. Patterns that help refine our models, improve our predictions, deepen our understanding of these ancient frozen worlds. The Atlas fragments eventually faded from view, their small comas dispersing their surfaces darkening as volatile ices sublimated away, leaving only dust and rock behind. By June 2020, even professional telescopes struggled to detect them. The fragments continued on their trajectory, swinging around the sun, heading back out toward the outer solar system. But now, invisible, silent, their moment in the light ended. But the data remained. Thousands of images, hundreds of spectra measurements of brightness and color and position, archived in databases that researchers would continue to analyze for years. The fragments themselves might have disappeared, but the information they revealed, the glimpses they offered into cometary structure and composition, that knowledge would endure. And somewhere in that knowledge lay clues to Atlas's ultimate mystery, hints about where it came from, what it was made of, and what that composition might reveal about the place and time of its formation. Chemistry written in ice tells stories that rock and metal cannot, stories about temperature and pressure, about the conditions present when molecules first froze into solid form, about the journey those molecules took before becoming part of something we might one day call a comet. Every atom in a comet nucleus was born somewhere else, forged in stellar furnaces, or created in the violence of supernovae scattered into space, and then gathered again by gravity into new configurations. The specific molecules those atoms form, the ratios in which different compounds appear, the isotopes present and their abundances, all of these carry information about where and when the assembly happened. For Atlas and comets like it, reading that chemistry means reading a diary written billions of years ago in a language we're still learning to interpret. Water ice dominates most comets, often comprising 70 to 80% of the nucleus mass. But this isn't the pure crystalline ice you might find in a glacial stream or frozen lake. Research shows that cometary ice formed at temperatures below minus 150 degrees Celsius, so cold that water molecules don't have time to arrange themselves into the orderly hexagonal structure of crystalline ice. Instead, they freeze into amorphous ice, a disordered solid where molecules are randomly positioned more like glass than like the ice cubes in your freezer. This distinction matters because amorphous ice can trap other molecules within its structure, essentially creating a molecular cage that holds volatiles like carbon monoxide, methane, and noble gases. When the ice eventually warms and transforms to crystalline structure, those trapped molecules are released, sometimes suddenly creating outbursts of activity that can brighten a comet dramatically over the course of hours or days. Scientists suggest that the presence of amorphous versus crystalline ice can indicate formation temperature. Very cold environments favor amorphous ice. Slightly warmer conditions, though, still far below freezing by Earth standards, allow crystalline ice to form. By studying the phase of ice in comets, researchers can infer something about the thermal environment where the nucleus originally assembled. For water itself, there's another layer of information encoded in isotope ratios. Most water molecules consist of 2 hydrogen atoms and 1 oxygen atom, H2O. But about 1 in every 6,400 water molecules on Earth contains deuterium instead of regular hydrogen in one position. Deuterium is heavy hydrogen with a neutron added to the nucleus, and its presence in water creates a molecule called HDO, or heavy water. The ratio of HDO to H2O varies depending on where and how the water formed. Research shows that water formed in very cold environments tends to be enriched in deuterium because the heavier isotope condenses more readily at low temperatures. By measuring the DH ratio, the deuterium to hydrogen ratio. In cometary water, scientists can infer formation conditions and potentially trace the water's origin. Earth's oceans have a specific DH ratio, about 156 parts per million. If comets delivered water to early Earth, as many scientists believe they did, then you'd expect cometary DH ratios to match Earth's oceans at least approximately. But measurements have shown considerable variation among comets. Some match Earth's ratio closely. Others show enrichment factors of 2 or 3 times higher, suggesting they formed in colder regions or from material that had a different thermal history. The question of whether comets brought Earth's water remains open, complicated by these variations, and by the realization that asteroids, particularly those from the outer asteroid belt, might also have contributed significant amounts of water to early Earth. The chemistry points in multiple directions, suggesting that Earth's oceans might be a mixture water from several different sources, combined over billions of years of impacts. Beyond water, comets contain a remarkable inventory of other ices and frozen gases. Carbon dioxide, CO2, often comprises 5 to 20% of the volatile component frozen solid at the low temperatures of the outer solar system. Carbon monoxide, CO, is present at levels ranging from trace amounts to more than 10% in some comets. The ratio of these carbon-bearing molecules tells us about the oxygen availability and temperature during formation. Methane, CH4, appears at levels typically around 1% or less, though some comets show higher abundances. Ammonia, NH3, is often present, but at very low levels, usually less than 1%. These molecules are chemically reduced, meaning they formed in environments where oxygen was tied up in other compounds like water and carbon dioxide, allowing carbon and nitrogen to bond with hydrogen instead. The presence of more complex organic molecules makes cometary chemistry particularly intriguing. Spectroscopic observations and direct sampling missions, like ESA's Rosetta, have detected formaldehyde, methanol, ethane, acetylene, hydrogen cyanide, and even more complex compounds. Some of these are considered prebiotic molecules, chemical precursors to the kinds of compounds necessary for life as we know it. Rosetta's mission to Comet 67P Churyumov-Gerasimenko, which orbited and studied that comet from 2014 to 2016, revolutionized our understanding of cometary composition. The spacecraft carried instruments capable of sampling the gas in the coma and analyzing it with unprecedented precision. Among the discoveries was the presence of glycine, the simplest amino acid, and phosphorus, an essential element for life, that had never been directly detected in a comet before. These findings suggest that comets might have delivered not just water to early Earth, but also the chemical building blocks of life itself. When you consider that Earth was heavily bombarded by comets and asteroids during its first billion years, that impacts were frequent and massive, it becomes plausible that much of the organic chemistry on early Earth came from space delivered in these frozen packages that vaporized on impact, but left their chemical cargo behind. The dust component of comets adds another dimension to compositional analysis. Research shows that cometary dust is primarily composed of silicate minerals mixed with organic compounds and sometimes metallic grains. The silicates are similar to what we find in asteroids and in primitive meteorites called chondrites, suggesting that the dust in comets formed in the same regions of the early solar nebula, where rocky planets and asteroids formed. The organic component of the dust is particularly rich and complex. Some of it takes the form of large carbon-rich molecules called macromolecular organic compounds, essentially complex tangles of carbon atoms bonded with hydrogen, oxygen, nitrogen, and other elements. These compounds are similar to kerogen, the organic material found in some Earth rocks, or to the complex organics found in the most primitive meteorites. There's also evidence for polycyclic aromatic hydrocarbons, or PAHs, in cometary dust. These are ring-shaped molecules made of carbon and hydrogen stable and common throughout the universe, found in interstellar space in star-forming regions and the atmospheres of planets. PAHs are interesting because they might have played a role in the origin of life, providing stable carbon structures that could serve as scaffolds for more complex chemistry. One of the fascinating aspects of studying cometary composition is how it varies from comet to comet. You might expect that if all comets formed in the same region of the solar system from the same material, they would all have similar chemistry. But observations show significant diversity. Some comets are relatively rich in carbon monoxide, others have very little. Some show strong ammonia emission, others show almost none. The deuterium to hydrogen ratio varies by factors of 2 or 3 among different comets. This diversity suggests that the region where comets formed wasn't uniform. Different parts of the solar nebula, the disk of gas and dust from which our solar system formed, had different temperatures, different pressures, different abundances of various molecules. Comets that formed closer to the Sun would have different chemistry than those that formed farther out. Material that was processed through the hot inner regions and then transported outward would differ from material that stayed cold throughout. There's also the possibility of mixing. As planets formed and migrated, they stirred the solar nebula, moving material around, creating turbulence that could transport ice particles from one region to another. A comet might contain ice grains that formed in several different environments averaged together into a composition that doesn't match any single formation location perfectly. For Atlas, the compositional data suggested chemistry broadly consistent with Oort cloud comets, but with some interesting variations. The carbon monoxide content appeared somewhat elevated compared to typical values, though not as extreme as in 2I Borisov. The water production rate and dust-to-gas ratio fell within normal ranges. Spectroscopic observations showed evidence for the usual suspects: cyanide emission carbon-bearing molecules, silicate dust. But the fragmentation complicated detailed analysis. As pieces broke off and exposed interior material, the observed composition changed slightly, suggesting that the nucleus wasn't uniform throughout. The interior appeared richer in volatile ices, particularly carbon monoxide, while the surface was more depleted, consistent with a comet that had experienced some warming in its past, that had driven off the most volatile components from its outer layers. If Atlas was truly an interstellar comet, its composition would carry information about another stellar system entirely. The chemistry would reflect the conditions in that system's protoplanetary disk, the temperature and pressure gradients, the elemental abundances in the gas and dust from which planets formed. Comparing that chemistry to solar system comets could reveal whether planetary system formation follows universal patterns or whether each system has unique characteristics. Some theoretical models suggest that the basic chemistry of planet formation should be similar around all sun-like stars. The physics and chemistry are governed by fundamental laws that don't vary. So if the starting conditions are similar, the outcomes should be similar too. But other models emphasize the role of chance and contingency. Small differences in initial conditions can lead to large differences in outcomes through chaotic dynamics and feedback processes. An interstellar comet with measurably different chemistry from solar system comets would support the idea that planetary systems are diverse, that formation conditions vary significantly from star to star. A comet with similar chemistry would suggest universal patterns that the same processes produce the same results regardless of which stellar neighborhood they operate in. For Atlas, the answer remained tantalizingly unclear. The chemistry was similar enough to solar system comets that it could easily have formed in the Oort cloud. But it was different enough that interstellar origin couldn't be ruled out either. The data pointed both directions, refusing to commit to a definitive answer. This ambiguity is frustrating, but also scientifically valuable. It shows us the limits of what we can determine from remote observations alone. It suggests that confirming interstellar origin requires more than just chemistry. It requires trajectory data, precise enough to eliminate orbital uncertainties, or it requires catching these objects earlier when they're farther from the sun and less affected by outgassing forces. The chemistry locked in Atlas's ice told a story, but like many stories from the distant past, it was incomplete, open to interpretation, leaving room for different narratives depending on which details you emphasized. What was clear was that whether formed in our solar system or around another star, Atlas was made of the same basic materials that appear in comets everywhere we look, suggesting that whatever diversity exists among planetary systems, the fundamental chemistry of ice and dust remains remarkably consistent across the cosmos. Those consistent patterns point toward deeper questions about how common the ingredients of life might be, about whether the chemistry we see on Earth is unusual or universal about what we might find, if we could someday visit other solar systems and sample their comets directly. For now, we watch the visitors that come to us, reading their chemistry like messages sent across impossible distances, hoping each new arrival brings answers even as it raises new questions. For most of human history, we believe the space between stars was empty, a void, containing nothing but darkness, and perhaps some diffuse gas too thin to matter. We were wrong in ways we're only beginning to understand. The realization that interstellar space might be full of wandering objects, orphaned from their birth systems, and drifting through the galaxy, emerged slowly from observations that didn't quite fit from trajectories that seemed too open from velocities that appeared too high. But for centuries, the evidence was ambiguous, the calculations uncertain, the claims disputed. It took until the 21st century, until October 2017, for humanity to confirm beyond doubt that we detected our first visitor from another star system passing through our cosmic neighborhood. The story of that confirmation begins with a telescope on Haleakala in Maui, Hawaii. The Pan-STARRS 1 telescope, designed to scan the sky for near-Earth asteroids and other transient phenomena, detected on October 19, 2017, an object moving rapidly through the constellation Lyra. Initially cataloged as a comet given its distance and apparent motion, the object received the designation C2017-U1. But as observations accumulated over the following days, something unusual became clear. The trajectory was hyperbolic definitively. So, with an eccentricity of approximately 1.20, this wasn't marginal uncertainty straddling the boundary between bound and unbound. This was unambiguously an open orbit, an object moving fast enough that the sun's gravity would never capture it, never bend its path into a closed ellipse. C2017-U1 was passing through, arriving from the direction of the constellation. Lyra swinging around the sun and heading out toward the constellation. Pegasus, a journey of 26,000 light-years per million years, assuming it maintained its current velocity. Research shows that when astronomers traced the trajectory backward, they found no obvious parent star, no stellar system that the object's path intersected within the past several million years. It appeared to have been traveling through interstellar space for a very long time, perhaps billions of years, gradually drifting through the galaxy, until chance brought it close enough to our solar system to be detected. The discovery sparked immediate fascination. The object was reclassified from comet to asteroid and given a new designation, 1I 2017 U1, where the I stood for interstellar. It was also given a Hawaiian name, Oumuamua, meaning scout or messenger. In the Hawaiian language, acknowledging both its role as the first confirmed interstellar visitor and the Hawaiian location of the telescope that discovered it. But Oumuamua's nature remained deeply mysterious. Unlike typical comets, it showed no coma, no tail, no visible signs of outgassing as it approached, and then receded from the sun. Yet careful analysis of its trajectory revealed a small non-gravitational acceleration, a deviation from the path predicted by gravity alone, as if something was gently pushing it. For comets, such accelerations are common, caused by jets of sublimating gas acting like tiny rocket engines. But if Oumuamua wasn't producing visible gas, what was causing the acceleration, theories proliferated. Some scientists proposed that Oumuamua was composed primarily of nitrogen ice similar to the surface of Pluto, which would sublimate without producing the typical molecules that make cometary comas visible. Others suggested it might be a dark comet, producing gas at rates too low to detect from Earth's distance, but still sufficient to create measurable acceleration. A few researchers more speculatively wondered if the acceleration might indicate something artificial, perhaps a light sail, though this idea remained highly controversial and was considered the least likely explanation by most scientists. The shape of Oumuamua added to the mystery. Light curve analysis, studying how its brightness varied as it rotated, suggested an extremely elongated form, perhaps 400 meters long, but only 40 meters wide, a 10-to-1 aspect ratio, unlike any natural object previously observed. Some models proposed it might be disc-shaped rather than cigar-shaped, which would fit the observations equally well, but still implied an unusual geometry. Have you ever encountered something so strange that every explanation seems inadequate? That's what Oumuamua represented for the astronomical community. Every model explained some observations, but struggled with others. The object seemed designed to confound expectations to resist easy categorization. Then, less than 2 years later, came a second interstellar visitor, one that behaved much more conventionally. On August 30th, 2019, Crimean amateur astronomer Gennady Borisov discovered a comet using a 0.65-meter telescope he had built himself. The object, initially cataloged as GB0034, showed clear cometary activity, a visible coma, and faint tail. But like Oumuamua, its trajectory was hyperbolic, unambiguously unbound from the sun. The comet was redesignated 2I Borisov, humanity's second confirmed interstellar object, and observatories worldwide turned their attention to it. Unlike Oumuamua, which was discovered after its closest approach to the sun and was already racing outward, becoming fainter every day, Borisov was discovered while still approaching, offering months for detailed study before it faded from view. Scientists suggest that Borisov behaved exactly like a typical comet in almost every respect. It developed a substantial coma as solar heating increased. It sprouted 2 distinct tails dust, an ion, following the patterns seen in countless solar system comets. Spectroscopic analysis showed emission from cyanide diatomic carbon and water, the standard signatures of cometary outgassing. In many ways, Borisov could have been mistaken for an Oort cloud comet, except for its definitive interstellar trajectory. But the detailed composition analysis revealed intriguing differences. The ratio of carbon monoxide to water was unusually high, perhaps 3 to 10 times greater than typical solar system comets, suggesting formation in an extremely cold environment. The dust-to-gas ratio also appeared somewhat different, implying variations in the relative abundance of rocky versus icy material. These compositional differences hinted that, while the basic chemistry of comet formation might be universal, The details vary depending on the specific conditions in each protoplanetary disk. Borisov formed around another star in a disk with its own temperature gradient, its own elemental abundances, its own dynamical history. The comet carried chemical fingerprints of that alien environment, subtle variations from solar system norms that whispered of different formation conditions. The discovery of 2 interstellar objects within just 2 years suggested that such visitors might be relatively common. Prior to 2017, astronomers had predicted that interstellar objects should pass through the inner solar system, occasionally perhaps 1 per year or 1 per decade. But they had never been detected because their motions made them difficult to distinguish from solar system objects unless observed very carefully. Research shows that statistical models based on the detection of Oumuamua and Borisov suggest there might be thousands or tens of thousands of interstellar objects passing through our solar system at any given time. Most of them too faint or moving in trajectories too similar to bound objects to be easily identified. The vast majority pass through unnoticed invisible wanderers, whose presence we can infer statistically, but cannot observe directly. This realization transforms our understanding of interstellar space. Far from being empty, the volume between stars is populated by a vast diaspora of orphaned worlds, ejected planets and comets drifting through the galaxy. Some estimates suggest there could be more mass in these rogue objects than in all the stars combined, a dark population of exiles moving invisibly through the night. For every Jupiter that remains in a stable orbit around its star, perhaps a dozen Jupiter-mass planets were ejected during formation, sent wandering into interstellar space where they cool gradually over billions of years, possibly retaining subsurface oceans heated by radioactive decay long after their surfaces freeze solid. For every comet that remains in a stellar Oort cloud, perhaps 1,000 were ejected scattered by gravitational interactions with forming planets or passing stars. These objects follow galactic orbits, moving at typical stellar velocities of tens or hundreds of kilometers per second relative to the galactic disk. Occasionally, by pure chance, their paths intersect the star system. Even more rarely, they pass close enough to that system's inner regions to be detectable by planetary civilizations capable of astronomical observation. We are such a civilization, and we're only now developing the tools to detect these visitors reliably. The next generation of survey telescopes, particularly the Vera C. Rubin Observatory, with its Large Synoptic Survey Telescope scheduled to begin operations in the mid-2020s, will scan the entire visible sky every few nights, detecting transient objects with unprecedented sensitivity. Scientists suggest that Rubin might detect dozens or even hundreds of interstellar objects per year, transforming these visitors from rare anomalies into a population we can study statistically. Each detection will add to our understanding. What's the size distribution of interstellar objects? Are most of them comet-sized, or are larger objects common too? What's the typical composition? Do they cluster chemically into families suggesting similar origins? Or is every interstellar visitor unique? How many show active cometary behavior versus inert asteroid-like characteristics? These questions matter because they relate to fundamental processes of planet formation and system evolution. The objects we eject tell us about the violence and chaos of planetary system birth. The compositions we measure reveal the diversity of chemical environments in protoplanetary disks. The detection rates constrain how efficient star systems are at retaining versus losing material. There's also a deeper philosophical dimension to studying interstellar visitors. Every such object is a physical sample from another stellar environment, a piece of another world that has traveled across light years to reach us. While we cannot yet visit other star systems directly, these visitors bring fragments of those systems to us, offering glimpses of planetary formation conditions beyond our sun's influence. For Atlas, the question of whether it belonged to this population of interstellar wanderers or was simply an extremely long-period comet from our own Oort cloud remained unresolved. The orbital data suggested possible interstellar origin, but didn't confirm it definitively. The chemistry showed some interesting variations from typical comets, but nothing definitively alien. Atlas occupied that frustrating middle ground, where neither conclusion could be reached with certainty. But perhaps that ambiguity itself teaches something valuable. It reminds us that nature doesn't organize itself into neat categories for our convenience. The boundary between bound and unbound, between native and visitor, between familiar and exotic, these distinctions matter to us, but not to the universe. Objects simply follow the trajectories. Physics dictates carrying the chemistry. Their formation conditions produced indifferent to our classifications. As detection capabilities improve, as surveys become more sensitive and more comprehensive, that middle ground will narrow. Future interstellar visitors will be caught earlier, tracked more precisely, analyzed more thoroughly. The questions we couldn't answer definitively about Atlas will find clearer answers in the visitors yet to come. And they will come drifting silently through the dark between stars, carrying their frozen archives of alien chemistry. Their trajectories telling stories of gravitational chaos, billions of years past. Their very existence proof that the galaxy is more connected, more dynamic, more filled with wandering worlds than we ever imagined when we first looked up at the night sky and wondered what lay beyond the light. The tools we use to study the universe are always evolving, growing more sensitive, more sophisticated, more capable of detecting the faint whispers of light that carry information across impossible distances. What we couldn't see a decade ago becomes routine. What we couldn't measure becomes quantifiable. And with each improvement in capability comes new questions we couldn't even formulate before. In the 2020s and beyond, comet science stands at a threshold. The next generation of telescopes and space missions will transform our understanding of these frozen wanderers, turning speculation into measurement, turning glimpses into detailed portraits. For objects like Atlas future visitors arriving on similar trajectories, we'll be able to answer questions that remained frustratingly ambiguous this time. Questions about origin and composition, about structure and history, about the diversity of worlds beyond our solar system. The Vera C. Rubin Observatory, scheduled to begin full operations in the mid-2020s, represents perhaps the most significant advance in survey astronomy in decades. Located on Cerro Pachón in Chile, at an elevation of 2,715 meters, where the air is thin and the skies are dark. Rubin will house the Large Synoptic Survey Telescope, equipped with the world's largest digital camera, a 3.2 gigapixel marvel capable of imaging the entire visible sky every few nights. Research shows that this comprehensive repeated imaging will revolutionize the detection of transient and moving objects. Every asteroid, every comet, every object that changes position or brightness will be automatically flagged by the survey's data processing pipeline. Scientists suggest that Rubin might detect tens of thousands of new comets over its operational lifetime, including dozens or perhaps hundreds of interstellar visitors like Oumuamua and Borisov. The key advantage is early detection. Both Oumuamua and Borisov were discovered relatively late in their passage through the inner solar system, after they had already made their closest approach to the Sun in Oumuamua's case, or with only months remaining for observation in Borisov's. Early detection catching these visitors when they're still far from the Sun provides much more time for detailed study, for coordinating observations across multiple telescopes, for potentially even sending a spacecraft to intercept them. Imagine if Atlas had been detected 6 months earlier, while still beyond the orbit of Jupiter. The fragmentation might have been predicted from compositional analysis. Observations could have been planned to capture the breakup in exquisite detail. The chemistry of the interior could have been measured before and after the fracturing, providing a complete picture of compositional gradients within the nucleus. Every question that remained ambiguous might have found clearer answers simply from having more time to observe. The European Space Agency's Comet Interceptor mission, currently scheduled for launch in the late 2020s, takes a different approach to the problem of studying pristine comets. Rather than targeting a specific known comet and traveling directly to it, Comet Interceptor will be placed in a parking orbit at the Sun-Earth Lagrange Point 2, about 1.5 million kilometers from Earth, where it will wait for a suitable target to be discovered. When astronomers detect a dynamically new comet, one making its first passage through the inner solar system from the Oort cloud, or ideally an interstellar visitor, Comet Interceptor will leave its parking orbit and intercept the comet flying through its coma and possibly deploying smaller probes to observe from multiple angles simultaneously. The mission is designed to study pristine material that has never been heated by the sun, never altered by previous close approaches. Material that still retains the chemical fingerprints of its formation environment. Scientists suggest that such a mission could definitively answer questions about interstellar comet composition that remain ambiguous from remote observations. Direct sampling of gas and dust, in situ analysis of particle composition, high-resolution imaging of the nucleus surface, all of this would provide data impossible to obtain from Earth-based telescopes, no matter how powerful. The technology for analyzing cometary material has also advanced dramatically. Modern mass spectrometers can identify individual molecules and their isotopic ratios with extraordinary precision. New spectroscopic techniques can detect molecules at concentrations too low to observe with older instruments. Computer models of comet structure and evolution have grown sophisticated enough to predict behavior based on initial conditions, allowing researchers to test hypotheses about formation environments by comparing predictions to observations. One particularly promising development is the use of artificial intelligence and machine learning in astronomical data analysis. Research shows that neural networks can be trained to identify subtle patterns in spectroscopic data patterns that might indicate specific molecules or compositional ratios that human analysts might miss. These systems can process vast data sets far faster than humans, flagging interesting objects for detailed follow-up, discovering correlations that weren't previously recognized. For comet science, AI systems could analyze thousands of cometary spectra, identifying families of objects with similar compositions, detecting outliers that might indicate unusual formation conditions or interstellar origin. As the number of observed comets grows into the tens of thousands with next-generation surveys, such automated analysis becomes not just helpful, but essential. No human team could manually examine every data set, but AI systems can triage the observations, directing attention where it's most scientifically valuable. The question of what we might learn from future comets touches on fundamental mysteries about planetary system formation and evolution. Every comet carries information about the conditions in which it formed, the temperature and pressure, the available materials, the dynamical environment. By studying many comets by building statistical samples large enough to reveal patterns, we can map out the diversity of formation conditions across our solar system and potentially across the galaxy. Do all solar systems produce comets with similar compositions, or does each system have unique characteristics reflecting its particular history? How common are interstellar wanderers, and do they cluster into families suggesting they were ejected from the same systems? What can the isotopic ratios in comets tell us about the stellar environments where their materials originally formed before being incorporated into planetary systems? These questions extend beyond pure astronomy into astrobiology, the study of life's origins and distribution in the universe. If comets delivered water and organic chemistry to early Earth, as considerable evidence suggests, then understanding cometary composition helps us understand the raw materials from which life emerged. If similar comets exist throughout the galaxy, delivering similar chemistry to other planets, then the building blocks of life might be universal, scattered everywhere by these frozen messengers. There's also the practical consideration of planetary defense. While most comets orbit far from Earth, occasionally, their trajectories bring them uncomfortably close. Understanding comet structure and composition matters for predicting behavior, for modeling potential impacts, for designing deflection strategies if a comet ever threatens Earth. The fragmentation of Atlas and similar comets reminds us that these objects are fragile, that they might break apart under stresses we don't fully understand, complicating any attempt to predict or alter their trajectories. Future missions might not just observe comets, but interact with them more directly. NASA's Deep Impact mission in 2005 deliberately crashed an impactor into Comet Tempel 1, excavating material from beneath the surface and analyzing the resulting debris cloud. The experiment provided valuable data about cometary structure and strength, though it also revealed how little we understood about the detailed mechanics of such impacts. The crater formed was much larger than predicted, suggesting the nucleus was weaker, more porous than models had assumed. Future missions might attempt to collect samples from comets and return them to Earth for laboratory analysis. Sample return missions have been successful for asteroids. Japan's Hayabusa missions brought back material from asteroids Itokawa and Ryugu, and NASA's OSIRIS-REx returned samples from asteroid Bennu. Applying similar techniques to comets would be more challenging because cometary material needs to be kept frozen to prevent volatiles from escaping, but the scientific payoff would be enormous. Laboratory analysis can reveal details impossible to determine, from remote observations, isotopic ratios measured to extreme precision, organic molecules identified unambiguously, mineral structures examined in electron microscopes. Think about what we could learn from a few grams of pristine cometary ice material that formed billions of years ago in conditions we can only infer indirectly. Every molecule would be a clue, every isotope a constraint on formation. Models every organic compound a hint about the chemical pathways that might lead to life. The samples would be priceless archives, frozen libraries containing information about the early solar system, perhaps about interstellar space, perhaps even about other stellar systems, if we're fortunate enough to sample an interstellar visitor. The integration of different observational techniques also promises new insights, combining optical observations with infrared spectroscopy radio. Observations, X-ray monitoring, when comets interact with the solar wind, all of these wavelengths reveal different aspects of cometary activity. Modern telescopes increasingly offer multi-wavelength capabilities, allowing simultaneous observations that capture the full picture of how a comet responds to solar heating, how gas and dust production varies with heliocentric distance, how the composition changes as different ices sublimate at different temperatures. For Atlas, observations were limited by the technology available in early 2020 and by the rapid fragmentation that made extended study difficult. Future visitors will be observed more comprehensively, tracked more carefully, analyzed more thoroughly. The questions Atlas raised will find their answers not necessarily from Atlas itself, but from the cumulative knowledge built by studying many such objects over decades of improved observations. There's something beautiful about how science progresses through this accumulation of knowledge. Each observation adds to the collective understanding, even observations of objects that fragment before, revealing all their secrets, even measurements that remain ambiguous, even questions that can't quite be answered yet. The partial answers become context for interpreting future observations. The ambiguities define what needs to be measured more carefully next time. The failures teach us about the limitations of current techniques and guide the development of better methods. Do you think we'll ever know with certainty whether Atlas came from another star system, or will it remain forever? Maybe a question mark in the archives. Perhaps future observations of similar objects will accumulate enough statistical evidence that we can say with confidence what fraction of such comets are interstellar versus extremely long-period natives. Or perhaps each object will remain individually ambiguous while the population statistics become clear. Either way, ATLAS has served its purpose. It captured attention, sparked curiosity, generated observations that contribute to our understanding of cometary behavior and fragmentation. It reminded us that the universe doesn't always deliver the spectacles we predict, that nature operates according to physics rather than human expectations, that disappointment and discovery often walk hand in hand. The tools we're building, the missions we're planning, the techniques we're developing, all of these represent humanity's determination to understand the cosmos more deeply, to read the stories written in ice and stone and starlight, to place ourselves in context within a universe far stranger and more wonderful than our ancestors imagined. Each new telescope, each new mission, each new technique brings us closer to answers, while simultaneously revealing how much more there is to ask. And somewhere out there beyond the orbit of Neptune, beyond the scattered disk and the Oort cloud and the vast dark between stars, other frozen worlds are drifting, following trajectories that will someday, perhaps, centuries or millennia from now, bring them close enough to our sun to be detected, studied, understood a little better than we understood ATLAS. The next wanderer is already on its way, though we don't know it yet, carrying its own frozen archive, its own secrets, its own questions for us to puzzle over. There's a certain poetry to incompleteness, to stories that begin with promise and end in questions to visitors that arrive unannounced and depart before we fully understand what they were or where they came from. ATLAS came to us in the final days of 2019, a point of light in Ursa Major that grew brighter with each passing night, carrying the possibility that it might be something extraordinary, a messenger from beyond our sun's domain. It carried our hopes for a spectacular spring display, for a comet bright enough to see in daylight, for a celestial wonder that might unite a world increasingly fractured by division and uncertainty. And then, in those strange early months of 2020, as human civilization confronted its own fragility, ATLAS quietly came apart, its nucleus fragmenting into pieces that dispersed along its trajectory, like memories fading into darkness. The disappointment was real. The anticipated spectacle never materialized. The questions about interstellar origin remained unanswered. The chemistry suggested both familiarity and strangeness, refusing to commit definitively to either narrative. ATLAS became a might have been, a cosmic promise, unfulfilled at least in the terms we'd hoped for. But in its breaking, ATLAS taught lessons more valuable than any light show could have provided. It reminded us that prediction is not the same as control, that mathematics describes what should happen, but cannot force compliance from objects governed by physics more complex than our equations capture. The universe operates according to its own rules, indifferent to our expectations, our instruments, our desire for clear answers. The fragmentation revealed interior structure, exposed material that had been hidden for billions of years, provided data that an intact nucleus would have kept secret. Scientists studying those fragments learned about cometary strength and weakness, about compositional gradients between surface and interior, about the processes that hold these ancient objects together, and the stresses that pull them apart. Every image of the break-in nucleus, every spectrum of gas from freshly exposed ice, every measurement of fragment separation, velocity added to humanity's collective understanding of these frozen worlds. Research shows that knowledge accumulates not from perfect observations of ideal objects, but from the patient assembly of imperfect measurements of real phenomena. ATLAS was real, gloriously and frustratingly real, behaving exactly as physics demanded it must not, as our predictions suggested it should. The gap between prediction and reality is where learning happens, where models get refined, where understanding deepens. Think about what ATLAS represented in a broader sense. Whether it came from our solar system's Oort cloud or from interstellar space, it was ancient beyond easy comprehension. The ice in its nucleus formed when our solar system was young, or perhaps when some other star system was organizing itself from a cloud of gas and dust, light years away. Either way, that ice predates everything human, every civilization, every written word, every thought anyone has ever had. It drifted through the dark for eons, slowly cooling, slowly accumulating cosmic ray damage patient and eternal until it wasn't. Until warmth and stress exceeded strength and the structure that had endured for billions of years came apart in a matter of weeks. There's something profound about that juxtaposition, about the contrast between deep time and sudden change, between the patient preservation of the cold dark and the violent disruption of approaching light and heat. We are, in some sense, much like comets ourselves. We exist in a universe that formed long before us and will continue long after we're gone. We're held together by forces we don't fully understand, chemistry and physics, and the mysterious emergence of consciousness from matter that by all rights should be inert. We drift through time, mostly stable, occasionally fragmenting under stresses we didn't anticipate. And we carry within us information about our origins, chemical signatures of the conditions that allowed us to form isotopic ratios that tell stories about stellar nucleosynthesis, and supernova explosions that created the elements in our bodies billions of years before Earth existed. The connection between comets and life runs deeper than mere metaphor. Scientists suggest with considerable evidence that comets likely delivered much of Earth's water and organic chemistry during the heavy bombardment period of our planet's youth. The oceans you drink from, the carbon molecules that form the proteins in your cells, the nitrogen in your DNA, much of this may have arrived on comets that crashed into early Earth, vaporizing on impact, but leaving their chemical cargo behind to accumulate, to concentrate, to eventually participate in the chemistry that led to life. If Atlas was indeed an interstellar comet, then its organic molecules formed around another star in conditions we can only imagine. And yet those molecules would have been chemically similar to the organics in solar system comets, similar to the compounds that contributed to life on Earth. The implication is staggering. The chemistry of life may not be unique to our solar system, but may be universal, or at least common, scattered throughout the galaxy by wandering comets that deliver their frozen archives to any planet fortunate enough to intercept them. This means that life, at least in its chemical prerequisites, might be everywhere. Every stellar system that forms planets probably also forms comets. Every such system probably experiences a heavy bombardment phase where comets rain down on inner planets. The raw materials for life get delivered automatically, repeatedly, inevitably to countless worlds throughout the galaxy. Whether those materials successfully organize into living systems is a different question. But the ingredients are distributed widely, scattered by the same gravitational chaos that shapes planetary systems everywhere. Does that change how you think about Earth's place in the cosmos? We're not just inhabitants of one planet orbiting one star. We're participants in a galactic process, recipients of chemistry that may have traveled light years before arriving here, beneficiaries of organic compounds synthesized in stellar nurseries before our sun even existed. The atoms in your body are travelers, wanderers, veterans of journeys across space and time that dwarf any human voyage. Atlas, whether native or foreign, was part of that same story. Its ice contained water that might have been identical to water in Earth's oceans. Its organic molecules might have been indistinguishable from the organics that contributed to the first living cells. If it had struck Earth 4 billion years ago, instead of fragmenting in 2020, its contribution to our planet's chemistry would have been indistinguishable from the countless other comets that did impact during that era. It would have become part of Earth, part of the ocean, part of the atmosphere, eventually part of life itself. Instead, it fragmented and dispersed its material, spreading out along its orbital path, slowly fading as volatile ices sublimated away. leaving only dust and small rocky fragments that will continue their journey through space indefinitely. Perhaps someday, millions of years from now, one of those fragments will strike a planet or moon somewhere in our solar system. Perhaps some future geologist on some distant world will find that fragment embedded in rock and wonder about its composition, about its origin, about the story it carries encoded in its chemistry. The study of comets connects us to deep questions about existence itself. Where do we come from? How did life begin? Are we alone in the universe? What is our relationship to the cosmos that created us? These aren't just scientific questions, but philosophical ones, touching on meaning and purpose, and our place in a universe far vaster and stranger than our ancestors could have imagined. Atlas doesn't answer these questions, but it contributes to the slow accumulation of evidence that eventually leads to answers. Every comet observed every composition, measured every trajectory, calculated adds. Another data point to the grand project of understanding the universe and our place within it. The work is collaborative across time, with each generation, building on what previous generations learned, adding new observations, refining old models, asking questions that couldn't be formulated before. Future astronomers will observe comets we'll never see using telescopes we'll never use, asking questions we haven't thought to ask yet. They'll build on the work done studying Atlas and Borisov and Oumuamua and thousands of other objects. They'll have access to data we can only dream of, compositional measurements of extraordinary precision, structural information from close-up observations, perhaps even return samples from interstellar visitors. The questions that remained ambiguous for Atlas will find clearer answers through the study of future objects. But they'll also encounter new mysteries, new anomalies, new objects that don't quite fit existing categories. That's how science progresses, not by answering all questions and reaching some final understanding, but by asking better questions, by discovering new phenomena that require explanation, by perpetually pushing at the boundaries of knowledge and finding that those boundaries simply recede, revealing more to explore, more to understand, more to wonder about. What will the next interstellar visitor reveal? Will it arrive as a comet like Borisov, behaving predictably, offering clear chemical signatures of its alien origin? Or will it be strange like Oumuamua, resisting easy categorization, sparking debates that continue for decades? Or will it be something else entirely, something we haven't imagined yet because we've only seen 2 confirmed examples and therefore have no sense of the diversity that might exist? The next visitor is already out there, drifting through the dark between stars or falling inward from the distant Oort cloud, its trajectory determined by gravitational interactions that happened millions or billions of years ago. We don't know when it will arrive, don't know what it will look like, don't know what stories its chemistry will tell. But it's coming as surely as tomorrow's sunrise, because the universe is vast and full of wanderers, and our solar system lies in their path. When it arrives, we'll watch it with whatever tools we have available, we'll measure its composition and trajectory, we'll debate its origin and significance, we'll hope for spectacular displays, while preparing for more fragmentations, more ambiguities, more questions without immediate answers. And we'll learn, as we learned from Atlas, that the universe doesn't perform for us, but simply reveals itself according to physical laws we're still working to fully understand. There's a humility in that, a recognition that we're observers of processes far older and larger than ourselves, processes that will continue long after human civilization has faded to dust, long after Earth itself has been engulfed by the sun in its red giant phase billions of years from now. The comets will still be there, drifting through the dark, carrying their frozen archives, occasionally warming near a star, and briefly glowing before returning to the eternal cold. Atlas glowed for a few months in early 2020, brightened our telescopes, if not quite our skies, taught us lessons about fragility and uncertainty, and then faded back into the darkness from which it came. Its fragments continue outward, invisible, now silent, forgotten by everyone except the researchers who still analyze the data, who still publish papers about composition and structure, who still wonder about origin and meaning. But the story isn't over, not really. It continues in every comet yet to be discovered, in every observation, yet to be made, in every question yet to be asked. The story of Atlas is part of the larger story of how humanity slowly, patiently, carefully learns to read the universe, to interpret the messages written in light and ice and stone, to understand our place in a cosmos that generated us from stardust and gave us the capacity to look back at our origins and comprehend, at least dimly, the processes that made us possible. We've drifted together through the story of Atlas, through its discovery, and brightening through the excitement of prediction and the disappointment of fragmentation, through the science that fragments revealed and the questions that remained unanswered. We've explored the composition of comets, the mechanics of their destruction, the history of interstellar visitors, the future tools that will deepen our understanding. Thank you for staying with me through this quiet journey, for lending your attention to a story about a comet that almost was about a visitor that might have come from another star, about ice and dust and the patient work of science. The cosmos continues its slow revelation, star by star, comet by comet, question by question. And we're fortunate to witness even a small part of that grand unfolding. There are more stories waiting in the darkness, more wanderers approaching more mysteries to explore. Perhaps we'll meet again when the next visitor arrives, when telescopes catch another faint point of light moving against the stars, when calculations suggest another possible messenger from beyond our sun's domain. Until then, keep looking up, keep wondering, keep asking questions. The universe is vast, ancient, and full of wanderers, and so in our own way are we. Sleep well. Dream of distant stars and frozen worlds. Good night.